This webinar covers the third step with respect to our recommended workflow as implemented in Delta 2D and described in our Getting Started guide. After having set up the project, warped the images, and then of course created a fused image, it's now to detect and quantify spots. This is what we will talk about, and related aspects such as what can be done with the quantitation table, what is available there, what is normalization and standardization. The covered topics in a nutshell are spot detection. Is it influenced by the display of gel images? How can I display them? Then we talk about spot detection parameters and how they influence the spot detection itself. Then we will cover spot editing, talk about the importance of spot boundaries, and then how to cancel, split, add or merge spots. After that, spot transfer will be done and the benefit of it will be described. Then we will talk about the quantitation table, as I mentioned, about the different types, what we can do with columns and rows, how to control visibility and create individual customized tables. Normalization as the basis for good analysis is then explained. Two different kinds of normalization, one based on the other, and then I will just give a short explanation about standardization, which is also an important step for advanced statistics. The starting point of this webinar today is the fused image. We will use union fusion and to get all the spots of the experiment in one view. Union fusion means that each pixel is compared to pixel across all the images, and it appears in the fused image with its darkest appearance. That means also that the standard images in the Deutsch approach, that typically the G100 or Sci2 images, can be excluded and should be excluded from the image fusion because they do not provide additional information. In the best case, they just display the average spot intensity across all the images, and that means that they shall be weaker by definition than on at least one of the sample images. So standard images do not provide additional spot information compared to the real sample images. The fused image can also serve as a proteome map, and that is why we are using it. We can do the spot detection on it, and we can do it just once across the complete experiment. The proteome map is also the basis for visualization, which is covered by a different webinar when we're talking about presentation technologies in Delta 2D. Before going to the spot detection, let me briefly show our sample experiment that we will use today. It's the Deutsch experiment, which comes with each demo installation of Delta 2D, which each installation as a demo project for a multiplex approach. It includes 3 groups, one group for 3 replicates of sample A, 3 groups of sample B in a second group, and 3 replicates of the internal standard. That means we have a total of 3 gels with 3 images of each gel. Delta 2D has created an additional group called fused images, and that is the fused image. Inside I can just open it and show it. It is looking like a real gel image. Spot detection as the next aspect that we want to talk about today. Spot detection, of course, is based on a certain image, and depending upon how we display the image, the spot detection makes more or less sense from a subjective point of view. So depending, for example, on contrast settings, a certain spot is convincing to be a spot or not. To control spot detection, we can also have a look at gel image regions. That means the same area across all the images to just control whether what we see on the fused image really reflects the reality on the real sample images. Spot detection is controlled by a small number of parameters. They are by default chosen by Delta2D for each individual gel image, by the way, automatically, to be rather sensitive and to find if in doubt more spots than you want to see, because we thought it's much better and easier to eliminate or cancel false positive spots rather than to manually add all the spots that haven't been detected at all. The parameters address different aspects of spot detection. One is addressing background subtraction. It is called local background region. Another one is addressing noise sensitivity. The parameter is called average spot size. And the third one addresses the spot intensity. It's called sensitivity in percent. An additional option is controlling whether you like to get smooth spot shapes, and we recommend to keep that activated. By default it is activated, and you can just leave it as it is, which in most of the cases is true for all the parameters that have been proposed by Delta2D. Usually they work really nice, but of course it's up to you to change them. Let's see how this is working on our fused image. If I choose the spot selection tool in Delta2D but don't have spots at all up to now, then I'm asked to detect the spots on this image. I want to do that, and then I get this spot detection dialog offering the set spot detection parameters. They come with a short description each. You can read that later on your own if you like, and you can of course change these parameters as you like. If you have changed them to your own values, for example, if I double the average spot size and do a spot detection, I can later on get back to these originally proposed parameters by just clicking here, and then Delta2D is defining the automatically suggested spot detection parameters again, so that you can reuse them. A spot detection can be done as often as you like, so you can play with these parameters, change them, increase them, and just observe the effect of your changes. To really understand what each parameter is meaning, you should change only one at a time, run the spot detection, and then see how the detected spots have changed. I just click OK, and then the spots on this fused image will be. We will see a spot pattern now on this image, including a lot of spots. The first thing that we can do with spots, of course, is canceling them. Usually on gel images we have such a front at the left and the right. This is where the IPG strip is ending, and also on the bottom this is where the gel is ending, and of course you image them because you want to see the whole image in the software. I can easily delete or cancel these spots. For example, I can just click them and press the delete key. I can also select more of them by pressing the control key, or I can just drag a rectangle to select multiple spots and then either press the delete key or right click here and choose cancel spots from the context menu, and then they are gone. I can do this for any area that I like to do it, like this. Now I have selected spots that I do not like to cancel. I press the control key to unselect them again, like this, and to then delete with the delete key only the remaining selected spots. Here's one spot close to the border of the image. I want to delete this as well. So this is kind of cleaning work. However, there are also spots that are very weak. For example, in this region. Let us zoom in there and see. I just use the scroll wheel of my mouse and see there it seems to be no signal behind this spot area. But if we check for the contrast settings, we can see that we have the freedom to really change the intensity of the spots. This does not affect the quantities later on, but it's only for visualization. But if I now use this, you can see that there is a weak signal, so Delta 2D has detected this spot not by error, there is really a signal. And if I increase the contrast further, we will see that also for the other spots there is a signal which has been detected. And then of course it's up to you to say, this is not a real spot, I think this is just artifact or background. But this is something that we cannot decide for you. Let me relax the histogram, the contrast setting again. I press now automatic contrast setting just to fix that. And this is a new feature which is being introduced with version 4.3. Every newly imported image is now automatically contrast improved when importing it. Of course, you can change the settings by moving these sliders manually at any point of time. It's only for visualization, as I mentioned. You can change that anytime. It's just for the first impression of the images. So to now make sure that there are only relevant spots on the fused image, and you have to keep in mind that on the fused image each spot is appearing with its highest intensity across all the other images. And if it's weak on this image, it shouldn't be stronger on any of the other images. So you can almost be sure that if you delete a weak spot here, that you haven't cancelled a stronger spot on the other images then. So let us find out how to find a benchmark for weakness of spots. For this, I can open a table for the fused image. I just select this image and then choose the quantitation table symbol from the main symbol bar. I then rearrange the windows in a way so that I have access to this table and the dual view next to each other. And here you can see that we have a column called spot quality for the spots on the fused image. I can sort for this spot quality and then click on the first spot, which should be the worst spot. It shouldn't really look very nice because low spot quality means it doesn't look like a really nicely shaped spots in the 3D view. If I go to the other extreme, we also have spot qualities of 1, which is the maximum at the same time, like this or this. These spots are looking like real spots, and in between there is of course a certain gradient, and we can now go through all the spots, and you can see in the gel image regions the same spot selected on the fused image so that you have a look on the respective areas across all the other images. And then you can make your decision, is this a spot or not? And at a certain value of spot quality you will make the decision, okay, from now on higher spot qualities really show spots that I would like to keep. This is something that you have to find out on your own. And let me make this decision now here. And so I want to cancel all the spots with spot qualities of up to this value here. I have selected this spot. I scroll up to the top of the table, press Shift and click on the first spot to delete all, to select all these spots. And then I can just choose cancel selected spots, and now they are gone from the images, and I keep only spots with a spot quality higher than the one that I have observed. Of course, you can continue with canceling spots manually by selecting them, pressing the delete key. If you think, oh, this isn't really a good solution. I have cancelled spots that I would like to keep. You can make them visible again by choosing spots and then show cancelled spots. Then you see, hopefully you can see that via this session, you can see the spot boundaries with dotted lines for the cancel spots. You can select such a spot, right click it and remove the cancel flag of the spot so that it is back again with a solid boundary. And if I then hide all the cancelled spots again, this spot is back again. Let's now talk about spot editing. Spot editing means we want to shape the spot boundaries in a different way. This could be by splitting, adding or merging spots. We already have cancelled spots, and first we have to have a look at spot boundaries. What does that mean to have a spot boundary? The spot boundary is defining the area in which a spot quantity is measured. The absolute spot volume of a certain spot is calculated by summing up all the gray values within its spot boundary. And that is why we say we do not want to offer a certain painting tool where you paint a spot boundary just as you like it, or a knife so that you cut spots in a way that you like. We want to make it as easy as possible and as reproducible as possible, so you just let the software know where you want to have an additional spot or you want to have a spot split from another one, and delta to D is then calculating the spot boundaries as it is doing it always. So now coming to spot editing, let me close this table. Let me also zoom out, because now we want to see whether the spot detection for the spots that we have detected has been working properly. We can zoom into a certain region where we might have a problem, for example these spots here. Let us look here, and in fact we have a spot detection problem here. Maybe this spot is 2, and we have a look at the gel image regions view. Indeed, on the sample images we have 2 spots but not 1. The same applies here. We have 2 spots and should split this spot in 2. We do this using the spot editing tool, which needs to be loaded, and then we can just click on the additional spot, and then delta to D is defining the spot boundaries automatically. The same applies here, and we could also add a spot if it hasn't been detected yet. If you would say there is a spot here, you would just click there and delta to D is then forced to define a spot boundary here. I can right click on such a spot marker, as we call them, to delete it again. Let's also add 2 spots here in this region, and then of course we can and we should have a look across the complete image systematically. For doing this systematically, we also have this navigator roll-up. Here's the rectangle of the currently displayed part of the image, and then you can move this across the entire image so that you won't forget a certain area. And then, for example, click here and here to split the spot into different fractions. Another thing that we can do with spot editing is to merge spots. If you want to sum up modifications, for example, we could just, for example, paint a line here, and then all these spots will be quantified together. They are summed up. Let me right click again to delete this marker and get back to the original spot detection. So this way, do it systematically, invest the time which is necessary to do this, and make sure that you did not forget a certain region on the image. Invest some time, because you save a lot of time, since you have to do this only once, regardless of the size of your experiment. So even if you have 50 images in your experiment, or maybe 150, You just have one fused image on which you do the spot detection and optimize the spot pattern then. So let's go back to the presentation and coming to the spot transfer. What we have created on the fused image is the consensus spot pattern, and we want to apply it to all the other images, to all channels on all gels. This will result in the same number of spots and also in complete spot matching, and it will take us just a few seconds. Have a look at this. We have detected the spots on the fused image now. I hope that you can see these weak borders, and then this spot pattern is transferred to the other images, of course with respect to the warping transformations, so that they are really aligned properly and matched properly. So every spot on the fused image will now have a sister spot across all the other images. On each other image exactly one sister spot, so that we will get a unique spot matching and complete spot matching across all the different images. And this is increasing statistical significance. It wouldn't make sense if you run replicates and then do not get quantities for all the spots across all your replicates. Then you do not make use of the replicates, because you do replicates to increase statistical significance, to make sure that your expression ratios that are of interest for you are really true and not just random. That's why you do replicates, and we, with our approach, we make sure that these replicates are really used. Let's do this in Delta 2D. Here's the button, the symbol for transferring spots. I just click that. We have the choice which image we want to use as the basis, where we have the spot pattern, the consensus spot pattern detected. It's just one image in this example. And then we want to transfer it to all the other images. Of course, we cannot transfer it to the same image where they come from. I want to transfer the spots, and this takes just a few seconds. And as you can see in the gel image regions view, the spots show up on all the images one by one. Now also to the standard side images which are not visible in this gel image regions view here. Now spot transfer is done, and we have the same spot pattern applied to all the images. At the same time, the spot boundaries have been adapted to the target images, because a spot has different intensities across the images, and it wouldn't make sense to really use the same spot shape across all the images. Smaller spots demand for smaller spot shapes. And this can be controlled. You can, of course, switch off this possibility in the options for the spots. You can deselect this checkbox to remodel spots after transfer. We do not recommend this, because from our point of view, this does not make sense. We always want to quantify the same fraction of a spot, and for this we have to remodel the spots. Another option is the modeled spot shape extent. This is saying how large should a spot boundary be. You can, of course, play with this parameter also. If you change that in the next spot detection that you will do, of course on the fused image, this new parameter, if you change it to 70%, will result in smaller spot shapes in general for each spot. So they are closer to the visible signal. So this is just a question of what you like. We recommend to use larger extents because you want to quantify the complete spot in the optimum, but in some cases it might make sense to just have smaller boundaries, and then you can change this parameter before doing the spot detection, of course. Of course, you can set it back to 90% and do the spot detection once again. You can repeat spot detection as often as you like. You can also improve the spot pattern on the fused image. If you later on see, oh, I should have split another spot, do that, but then repeat the spot transfer also, because it is not automatically updated. So you will have to run the transfer after having changed the spot pattern on the fused image. As I said, when having transferred the spots, also the spot boundaries are adapted, and within each spot boundary, as we have said before, the quantitation is done. This is done automatically, and having all the spot boundaries, having all the spot quantities, having all the spot matches, because we know about which spot is the sister spot on which other spot on the other image, on the other images. Then the quantitation table can be constructed. This is also done automatically, and we can just open it and see what we can do with the different columns and rows. Opening the standard quantitation table is done via the window menu item quantitation table. We get two kinds of tables. One is the statistics table for group values. That means mean, standard deviation, and then ratio between groups and the p-value comparing groups with each other. And also an all gel images table containing data for single images. The statistics table, of course, is more and more useful when having replicates. You do not want to have a look into the detailed view of single images. More often you will use the means, compare the means. You want to analyze the ratios or p-values, or even use the statistical toolbox by pressing the Analyze button. But this is part of a different webinar where we cover advanced statistics and other things like that. So now we have a lot of tables, a lot of columns, and each column represents a certain attribute for a certain image or group. Here the mean, for example, you can resort. You can just move this column to a certain other position. That's up to you to define the order of the columns as you like. And we can also control the visibility of the columns and of images. Let me show this by clicking this visibility control dialog. Here, for example, we can now hide the fused image. The standard Site2 images are hidden by default since they do not contain quantifiable information. They are just necessary to adjust the quantities. We will see that later. But we can also hide other images if we like, or hide complete attributes like this, ratios, for example, average values, or display attributes that are not visible up to now, for example, the absolute spot volume, the background that has been subtracted, and so on. You can control the visibility of columns this way. Also in the statistics table, we have other attributes that are hidden by default. I press OK to hide the fused image now. Furthermore, we can sort the rows. Each row is representing a certain expression profile. We can sort the rows by, for example, the p-value. Click again to sort it the other way. You can click on mean to sort the table by this mean or by standard deviation. It's up to you to sort the table in a way that you like. We can also use filters. For example, we can use the p-value filter to filter out the boring expression profiles. We only want to see expression profiles, for example, that have a p-value of less than 0.05. And there is a counter. We only will keep 109 of 579 expression profiles by this criterion. I press OK, and then you will see that the visible number of expression profiles is decreased to 109. Of course, if you click here, you see the respective spot in the gel image regions view, but also in the dual view. The dual view is scrolled to this spot, and if you select multiple ones, then of course the complete range is then highlighted in the gel image regions view, but also in the dual view here. Excuse me, I have to close this dialog. Do this, okay. These spots are highlighted. All the other spots where we have signals are filtered out. They do not meet the criterion having a p-value of less than 0.05. So we have seen that there is two different types of quantitation tables, all gel images and statistics tables. In this statistic table, the first group in our project is the reference group. All the other groups are compared to this one and the p-value is shown for them. So I can now, let me first deactivate this filter, create a new quantitation table where the second group is the reference group. This can be done in the Project Explorer by just pressing or clicking first on sample B group and then sample A, or then sample C, D, E, F, G, whatever you have. So if you just select entire groups here and then press the quantitation table symbol in the main symbol bar, then we get a new quantitation table containing the groups that we have selected, with the first group that we have selected being the reference group for that. So all the p-values here and also ratios, I have hidden the ratios, sorry. Sorry, I didn't properly click here. Like this, no, okay. Now we get the ratio back. All the ratios and p-value columns are then calculated by comparing the respective group with this new reference group. And this is the one that I have selected first before opening this table. We can also open single images table if you, for example, click on a certain group and then on at least one single image or only on different single images like this, and then press this quantitation table symbol again, we get an all gel images table for single images values containing only the selected images. So this is rather flexible and very convenient to create tables according to your needs. You just have to be aware that if you define a filter, for example, in this statistics view, if you there define a filter for this p-value and then close this table, this filter is still active. And you might be curious, why are there so many spots hidden? I do not have activated a filter in my standard quantitation table. Then you would have to open this special customized table again and see that the filter is active there and deactivate it there. Yeah, the filters are not automatically deactivated when closing tables. Coming back to the presentation, I have already shown an example for filters. Of course, you can combine filters. You can combine that you want to exclude bad reproduced spots to concentrate on well-reproduced spots. So if you define a filter for the standard deviations for all the groups and limit standard deviation to 30%. Or you might just be interested in twofold changed spots, or you are maybe only interested in spots that have p-values smaller than 0.05. Of course, for a certain comparison of two groups. A filter is active until you deactivate it again. Visibility control, I have shown this in this dialog. You can also do this one by one for each single column in the dual view, in the quantitation table, sorry. There is a menu item columns, and here you have access to all the available columns, and you can activate or deactivate the visibility of each single column here as well. So then, having the quantitation table, we should know what has been done to calculate the normalized spot volumes which show up in this table. Normalization is necessary because different images might have different overall intensities. Possible reasons for that are different staining times or variations in exposure times. Both result in different intensity levels of the images without having different expression levels of the proteins. This can be controlled by normalization. There's a regular normalization. That means it's included in all available software packages. Normalization within each single gel image. That is done by just dividing a certain absolute spot volume by the sum of all spot volumes. And this results in the fact that the sum of all normalized spot volumes, the percent volumes, is 1. The sum of all these values is 1 after having normalized the spots. Now there are some options. We can change that behavior if we don't want to normalize against all the available spots. One reason could be, this is the first option of course, to keep the behavior of the software as it is. But a second option is to define a certain subset of spots to be the 100% that we want to use as the normalization basis as this term here. So these volumes shouldn't be the sum of all volumes available, but only some of the volumes, maybe 12, others 245, and so on. And these spots could be a list of suitable spots, for example, housekeeping or marker proteins, where you know these spots do not change in my experiment. They are really a stable basis for normalization. Or you could exclude varying strong spots. So you keep all the spots. In general, you keep all spots as 100%, but you exclude only those that are strong and change, because strong spots that change, of course, have a strong impact on the normalization. Here's a view on how it is done in Delta 2D. I will show that also. And there's a certain attribute for each spot, whether it should appear in the normalization basis or not. To demonstrate the effect of this normalization, we have prepared another small project. Let me open this one. It's just a small project with artificial images. Let me show this in the light table, like this. And as you can see here already, all the spots are constant. They do not change across all the images. There's only one spot in the center which has an increasing intensity across all these images. Now let's have a look at the quantitation table for all the gel images. As you can see here, all these spots that visually do not change their intensity change the intensity after normalization because of this strong spot, which is part of the normalization basis. The strong spot is this one, and if we exclude this spot from the normalization basis, here we have the normalization columns, and we can exclude all these strong spots from all the images by just pressing exclude selected spots from normalization set. And then you can see that the volumes of the other spots, which are still normalized but only against the spots that do not change too much, all these spots now have a real constant normalized volume. Only the strong spot is changing, and this is what we expect. So checking and controlling the normalization is important. Then there is another additional step for normalization in the Deutsch approach. For Deutsch, using the internal standard, at first this regular normalization, as I described, is done. You can also use the options that I have mentioned, but then a second step is added, and that means that each spot volume, each normalized spot volume on a Psi3 or Psi5 or G200 and G300 image is divided by the respective matched spot on the Sci2 or G100 image of the same gel. This is important. It's a normalization within each gel. If you divide the spot volumes this way and multiply them by 100, you result in the Deutsch normalized spot volumes for each spot on every Sci3 or Sci5 image. Of course, when doing this for the Sci2 images, you get always 100% for each spot volume, and this means these volumes do not contain good information for us. Here we do not have options. We can just use this normalization or not, and if you have a Deutsch project with internal standards, you should use this by defining the project to be a project using the internal standard. In Delta 2D, this is done in the project properties, and then this normalization step is done automatically. Of course, you also have to let the software know which image belongs to which gel. To check whether normalization is okay, you can use scatter plots. Let me go back to my original Deutsch demo project and then open any image and then show a scatter plot for these images. Scatter plot can be opened by using spots and then show scatter plots. And this is nicely because it's more or less symmetrically distributed around the 45-degree line. On one axis we have the volume on the one image, on the other axis the volume on the other image, and if the spots show up this way symmetrically around the 45-degree line, that means the spot volumes when comparing these two images are well balanced. This is shown in this presentation. Maybe here you see this shift. This means there is no good normalization. Here's another normalization strategy applied, and there you can see the complete cloud is shifted towards this direction, and you can make up your mind whether this is fine or not. Finally, I want to mention standardization. This is another step to process the data before doing advanced statistics. Imagine you have two expression profiles. These are the two, and obviously they are not the same here. One is contains much smaller spots than the other one. For this, we calculate the set score. For each single expression profile, we calculate a mean and a standard deviation, and then apply this formula to all the volumes, normalized volumes of a spot. For example, we have the quantities of these two expression profiles given in this table, along with the means and the standard deviations of these two expression profiles, and this is how these expression profiles look for. It's not obvious that they are similar to each other or whether they are similar because they have so different intensity levels. But if we apply the set score calculations, we result in this table. The mean is 0 and the standard deviation is 1 for each set score set of values. And then the new expression profiles have the same range, so they are mapped into the same data space, and that means that you can easily see that they have a certain identical dynamic behavior or very similar behavior. This makes them comparable, and then advanced statistic algorithms can really compare them and show them up in the same cluster, for example, or that they are similar to the same template that you apply, for example, in Pavlidis template matching. This is what I also want to show, and that means that these values are not the same as these. These are the values that show up in Delta 2D in the quantitation table, while these values show up in the statistical package. So don't worry if your values there are different to those that you know in the quantitation table. This is because of applying the set score calculation to the expression profiles. For Deutsch projects, since normalized volumes are ratios, as we have seen, every normalized volume is divided by the respective volume on the standard image. Every resulting normalized spot volume is a ratio, and that means we have to logarithmize to get a symmetric distribution of the data. And this is necessary before we standardize them and make them accessible to advanced statistics.